This video will cover additional topics about equations of a straight line, such as the distance between a point and a straight line, the equation of a straight line segment, and the relationships between straight lines. As always on this channel, you can expect a clear and concise explanation of each topic. But before proceeding, you must have knowledge of how to write equations of lines in three-dimensional space. Otherwise, you should watch the video that appears in the upper right corner screen before proceeding. Please don't forget to click on the like button, subscribe to our channel, and activate the notification bell. Your support is crucial for our channel's growth and enables us to continue creating quality content. Thank you in advance for your support. Let's begin with the equations of a line segment. A line segment is a section of a line bounded by 2 points. That is, a line segment is a piece or part of a line having 2 endpoints. Unlike a line segment has a definite length. Sometimes we need a description, not of an entire line, but of just a line segment. Let P be the initial point of the line segment, and Q be the terminal point of the line segment, and let R sub 0 and R be the associated position vectors. We know the equation of the line is given as follows. The position vector R is the position vector of any other point on the line. We can see that the vector v times t is the difference between the vectors r sub 1 and r sub 0. This equation can be rewritten in the form when t equals 0, we have r equals r sub 0, whereas when t equals 1, r equals r sub 1. Therefore, the vector equation of the line segment between points P and Q is given by this equation traces the line segment from P to Q whenever t varies from 0 to 1. We can also find parametric equations for this line segment, and the procedure is the same as when we obtained the parametric equations for the straight line. We now summarize the result as follows. The line segment from r sub 0 to r sub 1 can be described by the equations. Vector equation of a segment line, parametric equations of a segment line. Let's see how it works. Find a vector equation for the line segment from P to Q and the midpoint of the segment. Take the vector equation and observe that r sub 0 is a vector whose components are the coordinates of the initial point of the line segment, and r sub 1 is a vector whose components are the coordinates of the terminal point of the segment line. In other words, point P becomes the vector position r sub 0, and point Q becomes the vector position r sub 1. All we have to do now is rearrange the equation and subtract the components. The midpoint of PQ corresponds to t equals 1/2 because 1/2 times vector r is half the length of vector r. In other words, the midpoint of PQ is the terminal point of the vector position r when t equals 1/2. And of course, you could get the same result using the midpoint formula. Now you will learn how to calculate the distance between a point and a straight line in space. The distance from a point to a line is equal to the length of the perpendicular distance from the point to the line. In figure, let d be the distance between the point Q and the line L. Now let P be an arbitrary point on the line. Theta is the angle between the vector PQ and the line. Let the vector v be the direction vector of the line. We use the cross product between vectors v and PQ. The length of the cross product between the vector v and PQ equals the length of vector v times the length of vector PQ times the sine of the angle theta. But referring to the triangle, we see that the distance between the point Q and the line L equals the sine of theta times the absolute value of vector PQ. Hence, the sine of theta is the distance d divided by the absolute value of vector PQ. We can rewrite the equation below replacing the sine of theta with d divided by the absolute value of vector PQ. And finally, we obtain a general formula for the distance between a line in space and any point not on the line. We now summarize the results as follows. The distance between a point Q and a line in space is, where v is a direction vector for the line and p is a point on the line. Let us see how we can apply this formula to find the perpendicular distance between a point and a line in 3 dimensions. Find the distance between the point Q and the line given by the set of parametric equations. From the parametric equations, we can write the vector equation of this line. Now it is clearer the direction vector of this line and the point Q on the line. The figure on the side, together with the parallelepipeds, can help you visualize the distance between point Q and the straight line in space. We find the vector PQ by subtracting their corresponding components, and then we calculate the cross product between vectors v and PQ. The perpendicular distance d between the point Q and the line is given by the formula above. We divide the length of the cross product by the length of the vector v. Hence, the perpendicular distance between the point Q and the straight line is 2.3 units. Now let's study the relationship between two lines in space. But first, let's review the relationship between two lines in the plane. Given two lines in the two-dimensional plane, they are parallel but not equal if the distance between the two lines is fixed and the two lines go in the same direction. They will never meet. The lines are equal, also called coincident, if they are straight on top of each other. Both lines appear to be one line. Intersecting lines are lines that meet at a certain point. These lines might intersect at any angle, or they could be perpendicular. These relationships between the lines occur in the same plane, in three dimensions. A fourth case is possible. The rectangular box will be useful to understand the relationship between two lines in space. Given two lines in the three-dimensional space, they are parallel but not equal if the distance between them is fixed and the two lines go in the same direction. Straight lines are equal if they are straight above each other. Both lines appear to be one straight line, in the same way as two straight lines are equal in the plane. Intersecting lines in space are lines that meet at a given point, in the same way as they do on the plane. These lines can intersect at any angle, or they can be perpendicular. In three dimensions, a fourth case is possible. If two lines in space neither intersect nor are parallel to one another, are said to be skew lines. Skew lines can only exist in three dimensions. From our discussion of the relative position between two lines in space, we can conclude that to classify lines as parallel but not equal, intersecting, or skew, we need to know two things: whether the direction vectors are parallel and whether the lines share a point. If the direction vectors of line 1 and line 2 are parallel, then line 1 and line 2 are equal or parallel but not equal. If the direction vectors of line 1 and line 2 are not parallel, then line 1 and line 2 are intersecting lines or skew lines. Let's see how it works. From the parametric equations, we can write the vector equations of the lines. Now it is clearer their direction vectors and the point P on the lines. These vectors are not parallel, since neither is a scalar multiple of the other. Thus, the lines are not parallel. Because the direction vectors are not parallel, the lines are either intersecting or skew. To determine whether the lines intersect, we see if there is a point that lies on both lines. In other words, there would have to exist a single point such that its coordinates would have to satisfy the equations of both lines. And this leads to the following system of equations. You should be familiar with methods for solving systems of two linear equations in two unknowns. If not, you should watch the video that appears in the upper right corner of the screen before proceeding. To determine whether this system has a solution, we will solve the first two equations for t1 and t2, and then check whether these values satisfy the third equation. We will solve the first two equations by the method of elimination. We can eliminate the unknown t1 by adding the equations. We obtain t2 equals 0. We can now find t1 by substituting this value of t2 in either the first or second equation. Solving the second equation for t1, we obtain. We now check whether these values satisfy the third equation. Substitution into the third equation, however, yields a contradiction, and then these values don't satisfy the third equation. Since there is no single point that satisfies the parametric equations, these lines do not intersect, so they are skewed. We begin to solve this example in the same way as the previous example. From the symmetric equations, we obtain the vector equations of the straight lines. We observe that these vectors are not parallel, since neither is a scalar multiple of the other. So the lines are either intersecting or skewed. To determine whether the lines intersect, we see if there is a point that lies on both lines. We create a system of equations. We will solve the first two equations for t1 and t2, and then check whether these values satisfy the third equation. We obtain t2 equals 1 and t1 equals 2. We now check whether these values satisfy the third equation. We see that these values do satisfy the third equation, so the lines intersect. Substitution into the original equations yields the point of intersection. So the lines intersect at the point 4 minus 1 minus 5. These vectors are parallel because they are scalar multiples of each other. Thus, the lines are parallel, not equal. Here, it is worth adding that if the position vector r sub 0 were the same in both equations, these lines would be equal. Now, to find the distance between them, we can use the formula to calculate the distance between a point and a line. Let Q be a point on the line 1 and P a point on the line 2. We find the vector PQ by subtracting their corresponding coordinates. From now, the procedure is the same as the second example.